Hello, everyone. This is Teresa Connor again at One Water Solutions Institute at Colorado State University. And today we are hosting what's become a monthly webinar seminar on software tools that have been developed at CSU. And I'm going to start with just an introduction of the ERAMS technology for just a minute and then hand it over to Sybil Sharvelle, who's faculty here at CSU and the author of the Integrated Urban Water Model. So some background on ERAMS technology. It was started development in about 2008 as a cloud-based platform for researchers of all disciplines to share information in a cloud-based format on research projects to bring together disparate information sources to address different water and land challenges. And what's developed over time since about 2008 is a very strong network of disparate information sources that we tap into live. So we bring together all sorts of different climate, water, databases that are live, and we just have links into them so that you're tapping into live information, and it's GIS-based, so you can look at it spatially. There's a hydrology toolbox with watershed assessment programs and flow analysis tools. And today we're going to talk about some of our urban water management tools, one of which is the Integrated Urban Water Model. Dr. Sybil Sharvelle, faculty at CSU, is the author of that model and is going to take us through the development and how that model can be applied in different situations to look at scenarios for a potable water demand forecasting. So with that, I'm going to hand it over to Dr. Sharvelle.
Thank you, Teresa, and thank you for attending today. So today I'll be talking about the Integrated Urban Water Model, which, as Teresa already provided some background on, is intended to provide information on water conservation and reuse strategies, as well as water demand projections under different scenarios in the urban environment. So there are all sorts of water management strategies, water conservation and reuse strategies that are currently available as tools to reduce demand for potable or municipal water within an urban area. There's indoor and outdoor water conservation, so installation of water conservation fixtures in the home or use of more efficient water irrigation systems for out of the home, as well as changes in behavior related to irrigation or installation of xeriscape. Graywater reuse is a technology and practice that's growing in its use, and their water from laundry, showers, or bath waters can be used to meet typically non-potable demands, but potentially also potable demands. Stormwater can be also used, so roof runoff is a common one at the household scale, but larger projects are also possible where stormwater is collected more centrally and then reused. And then there's effluent reuse, so that's the use of treated wastewater and purple pipe systems. So there's all of these options available to utility managers and water managers. And there's a lot of interest in implementing these practices and potentially incentivizing these kinds of practices, particularly in areas of drought or where there may be insufficient water supplies. However, many questions still exist about these installation or promotion of these kinds of practices. So one of those is how much can demand actually be reduced at various levels of adoption of these practices? What are the most effective strategies to implement in my area? So in different climatic areas, different practices may be more effective than others, and so understanding that is a question that a lot of people have. And what are the most reliable strategies under climate change? So what are those strategies that can provide the most reliability and resilience of water supply systems moving forward? So the Integrated Urban Water Model was developed to forecast urban water demand and project potential savings from conservation and use of alternative water sources under varying climatic conditions and land uses. So what the integrated urban water model does is it makes use of some of these databases like Teresa was referring to, like land use, population, climate data, and uses those as in an automated way to limit user input of data to then run scenarios where a baseline projection of water demand can be created, and then further, various scenarios of water reuse and conservation can also be run. And ultimately, the output of it is a demand forecast for all of these different scenarios. So this is the IUWM interface. I'm not going to spend too long here because most of this webinar today will be focused on a demonstration of the integrated urban water model. The purpose of this introductory component is just to provide some background on how the model works and what it's intended to do. Okay, so all of the types of water management strategies that I've just discussed are included within the integrated urban water model, including the conservation and use of alternative water sources. So of note is various source water end use combinations can be investigated. So source waters include graywater, stormwater, and wastewater. And then end uses can include irrigation, toilet flushing, and even use for potable water, which is really gaining some traction and interest around the country. And in addition to running those scenarios, the water management scenarios, there's also potential to run climate scenarios and land use scenarios where the user can run future projections of climate, changes in temperature or precipitation, and also run changes in population, households, and then also land use types. So you can see you can change the low density development area to high density or medium density area and see what that impact may be. And we'll be running through some scenarios later where we actually demonstrate that. This figure shows an overall mass balance for the model. So the integrated urban water model is a mass balance based model. And you can see there's the various sources at the top, including supply of raw water. And then other sources could be treated gray water, treated wastewater, or stormwater. And then all of those different sources can be used to meet these demands that are in the yellow box on this page. So you can use those to meet potable demands or non-potable demands like toilet flushing or irrigation. And we also do have the potential to model CII demand, which is commercial, industrial, and institutional demand. That is kind of more specific, so the more simple runs of the model are really for estimating outdoor demand and residential indoor demand. So then from those different sources, we generate gray water and wastewater, and those can either be discharged or ultimately treated and sent back up to be included as a source water back up at the top. Okay, so like I said, the urban areas characterized first via these GIS interfaced databases that are available through ERAMs. So this is a really nice feature of the integrated urban water model because it means that the user does not have to input a large amount of data in order to obtain a reasonable estimate of demand in a certain area and then be able to run scenarios from that point. So this shows a user-selected area, and then there are these GIS-linked databases from NAR and PRISM, for example, for climate data, National Land Cover Data, or NLCD, for land use types, and then U.S. Census data is used for population and numbers of households. So ultimately, IUWM goes and retrieves data from those databases and then characterizes a particular urban area, and from the climate data, it can predict precipitation, solar radiation, and temperature, and from the NLCD data or land cover databases, percent impervious and pervious can be estimated, and then U.S. Census again is used for estimations of population and households. So from all of this characteristics of a certain urban area, you can now have an estimate of irrigation demand, stormwater, and indoor demand, and those are all then used to run these various scenarios within the integrated urban water model. So therefore, the user is basically getting most up-to-date data possible from these various databases. Again, these various scenarios can be run down to the block group scale, indoor demand conservation, and all of these scenarios can be run, and all of them at different levels of adoption and with different potentially storage tank volumes. So there's a lot of options within each of these scenarios that a user can select to customize what they would like to learn from the model. Okay, so the way that indoor demand is estimated is based partially, like I said, on the data from census on number of people populating a certain area, as well as the households. So we've used the residential end use study data from, a lot of that data came out of the Water Research Foundation. So there's the end use study that was published in 1999, and then another one that was recently published in 2016. And then there's some high efficiency data from homes that have installed highly efficient indoor fixtures. So what the user can do then is select a percentage of each of these types of homes. So average homes in 2016 is pretty representative of most urban areas currently. That's the most recent study, but in areas where you may have a lot of highly efficient water fixtures installed in homes, then you could increase the percentage of highly efficient homes. And otherwise, if you may have a lot of older construction and anticipate that not very many water conserving fixtures have been installed, you can customize that to be potentially a higher amount of homes in a certain area. Irrigation demand is really estimated from evapotranspiration, and we use the Hargreaves-Sermani method for that, and estimate irrigation based on a plant factor, and then the area that's irrigated based on the land use types that we have uploaded automatically from the National Land Cover Database. And this I just wanted to show, this is a recent verification of the Integrated Urban Water Model for the city of Fort Collins. And we'll be doing a demonstration for the city of Fort Collins today with the Integrated Urban Water Model. But here you can see, so what we have in the bottom x-axis here, there's 2013 data and 2014, and we have both simulated and observed data for the city for each residential indoor, observed outdoor, so that's total outdoor in the community, and then CII, which is again commercial, institutional, industrial. So for each of those, you can see the darker color of blue will be the indoor demand for that's observed versus the lighter color of blue is the model predicted value. So you can see that the model does a pretty good job of ultimately estimating these water demands within a particular service area. So with that now, I'm going to go ahead and move into a demonstration of the model. Okay, so I'd like to start here with the documentation page for the Integrated Urban Water Model. This page includes a description of the model, its purpose. It also includes a user guide, which includes a step-by-step procedure to go through Integrated Urban Water Model and develop a service area, then create estimates of baseline demand and water demands, and then look at these various scenarios. So there's step-by-step instructions for each of those different components of the model, and as you can see, there's also screenshots here to help guide that process along. So this is a great resource to use as you may be learning to use Integrated Urban Water Model, or if you kind of come across a problem while you may be running the model. Okay, so with that, then I will move now into the demonstration of the Integrated Urban Water Model. So we start here at this page, and you can see it is GIS interfaced with this map showing. And there's several ways. Our first step is really to create a service area. There's several ways that we can go about doing that. You can see all of those here in these areas here that we can select. I'm going to start with a simple rectangular selection because that is the quickest. And since we're going to be looking at Fort Collins today, we can zoom in using a zip code in that area, or you could also type in the city name. So now you can see that the city of Fort Collins has appeared on our map, and we could select a certain area of the city and run that. I'm actually going to cancel that right now because I would like to show how you can upload a boundary and actually have the water service area boundaries included and model that. So that's what I'd like to do for the demonstration today. And again, I'm going to go to upload a boundary, select my files, and this time it's getting those features, and I will type in the name of my service area, which is Fort Collins. And you can see now I can close this box now because it's uploaded this shapefile, and I now have the water service area for the city of Fort Collins uploaded into this. So we can now run different scenarios using the actual boundaries of the water service area. So the next step, if we look at number 2 over here on the side panel, is to select the analysis subunits. So we can run this as one single subunit. That's our first option here. So when we run as one single subunit, we're just collectively gathering the data or projections on water use for that entire area and then running scenarios for that entire area. However, IUWM also has the possibility to run at smaller subunits like the block group, or tract level. County level may also be relevant when you're doing more of a regional analysis. And that enables us to look at within each of those subunits, such as a block group, what the water demand projections are, and then how the scenarios would impact within those. So I'm going to run at the block group scale today. And then steps 3, 4, and 5 here are for selecting population, land use data sets, and climate data sets. So you can see here we have the potential to, the automatically uploaded data is U.S. Census data, and then NLCD for the land use data set, and then PRISM for climate. So those are, again, all automatically accessed. And so I'm going to just use those defaults today, but the user can also select other databases or even upload their own files if they may have better information locally. So I'm going to click Generate here, and now what IUWM is doing is that process that I had described before of going to these live databases and extracting the most recent data from those, and again doing that at, in this case, the block group scale within the Fort Collins water service area. So just extracting population now, and now it's creating this default scenario. So what it means by default scenario is using default values that are programmed within to the integrated urban water model. So I can now close this because the data extraction for this area was successful. And now I can go and either use the default, I can go ahead and run a default scenario, but most users would probably like to see what kind of data that default scenario is looking at and potentially even modify those. So we can do that within Edit. I just hit this Edit button, and we can see at the top here the current scenario that we're working with is the default scenario. So within this is the default values that the integrated urban water model utilizes to make estimates of both indoor and outdoor demand. So here you can see, similar to the PowerPoint file that I showed, we have percentage allocated of these average homes before 1999, 2016, and high efficiency. We found to just at 100% at this average homes built around before 2016 provides a pretty reasonable estimate of indoor demand, so that's the default value there. There's also some default values associated with the landscape irrigation. So for the first one is a temperature above which residents irrigate. So this is particularly relevant in an area like Fort Collins, where you may have seasonal irrigation and users turn off their irrigation at some point. Even if you have this set to something, this is set to about 14 degrees Celsius currently. If there's an area that doesn't experience that kind of seasonal change, this would still work because typically they don't go below this average daily temperature of 14.2 degrees Celsius. So then also within each of these land use types, there's an area that's irrigated, and these are default values based on National Land Cover Database recommendations for pervious and impervious within the various land use types. So I'm going to be using all default values today, but before we run the scenario, I would like to point out some users might be interested in evaluating or changing things specific to the subunits. So remember here we're running at the block group scale, so each block group has a GeoID that's listed over here on the left side. Then associated with each of those block groups, you can see the data that has been automatically generated through those databases like population, number of households, the open space area, medium density area. So if a user wanted to, they could look at even potentially changes in low density or high density area within a particular subunit and how that would have an impact, or just modify the subunit data with data that they may have locally that is improved from what's provided through the databases. So again, I'm not changing anything right now from the default. We're going to go ahead and run that. So I'm going to go ahead and click Save, and my scenario data is saved. And now I can, so remember, I've added actually no input into the model. I'm just running default values and all of the data that's automatically been generated through these databases. So now I can click Run, and here I can click or select what years I would like to run the model for. So in this case, I'm going to go ahead and select from 2005 through 2015. And down here is a list of outputs that can be selected to be more tailored. Today we're just going to run the typical outputs, which are what most people would be interested in, which is indoor demand, outdoor demand, wastewater produced, and things of these sorts. So now we're running this model. Integrated Urban Water Model is going and running the model at the block group scale for all of these different subunits individually. So it's now finished that execution. So we can close this box. And now you can see all these spatial units, and we can actually click on them. They'll say the GeoID, average annual demand associated with each of those subunits individually, population in each one, and the population density. So another really nice feature of IUWM is its graphing capabilities, and ERAMs in general with the graphing capabilities. So I just clicked on the default scenario in all scenarios to generate this estimate, and we can see now we've generated here now our default scenario, and for all that time period that we have an indoor demand on this graph as well as an outdoor demand, and clicking on these you can actually see the actual values. There's some nice features to download the graphs as well as the output data that's been generated for those, so that you can have a lot of ways to utilize that data. So we can, I oftentimes like to look at different time steps, so I like to look at the monthly average. And we can see here the outdoor demand is very substantial in the city of Fort Collins, which is the way that things are within the city because of the high irrigation demand during the summer months. Now, what you see now that we've developed this graph is that even each of these subunits is color-coded so that you can kind of identify based on the color how much water usage is happening in each of those various subunits. And I even can click on these subunits and look specifically within each of those subunits how those demands may vary in those subunits. So let me go back. So now that I've been clicking on those subunits, I can go back and look at the whole model, all of those combined together. And there's some features also to normalize the data. So we can normalize the data to population, for example. So now we're looking at per person water usage in gallons, and then per area of water usage. So these can also be useful for making some comparisons. All right, so now that I have generated this default demand, which in this case will serve as our baseline demand that we're going to be evaluating, I can now go and start generating scenarios. And I'm going to first generate some scenarios of water conservation and reuse strategies, and then I'll generate a separate set of scenarios for population growth and climate so that you can see all of those and how they work. Okay, so in order to do that, we go back into Edit. And I am going to now create a scenario. So the name of the new scenario, we'll do high efficiency homes. Okay, so in this scenario, we are going to make the assumption that there'll be conversion of a large number of homes from these average 2016 values to high efficiency values. So now we can modify, I'll say there'll be 20% of the homes will now be using 138 gallons per household per day, and 80% will move into this high efficiency area with 112 gallons per household per day. So now I don't need to click on Save to save this scenario data. As long as I've entered data while this high efficiency homes title is up here in my scenarios, that data is automatically going to save to that scenario. And then I can create a new scenario. So the next one I will look at is Graywater Reuse. Okay, so for Graywater Reuse, now we are going to go into the Practices tab here. And you can see under this Practices tab, we've got graywater, stormwater use, wastewater reuse, irrigation conservation, and projections is where we can get into some of the projections with population growth and land use change. So like I said, we're going to first start with graywater here. And we're going to need to fill in the percentage of graywater available for indoor residential and outdoor reuse, which we'll say is 100%. We'll assume 100% of the graywater could be used. And we're not going to model CII graywater reuse, so we're going to keep that at 0%. And like I said previously, there's the potential within IUWM to look at any source water end use combination. So we can look at all of these various different end uses for graywater. For now, I'll focus on the non-potable demands, and I'm going to assume a pretty aggressive adoption strategy just to look at what happens with that. So I'm going to assume 80% adoption of that strategy, and storage volume of 150 gallons per day per household. So that's a very reasonable storage capacity for a graywater system in a household. Now, of note is that in a multi-residential unit, each residential unit is counted as a household. So in a multi-residential unit, this would mean that per residential unit, there would be 150 gallons of storage. So that would be actually compiled over an entire multi-residential unit for a larger storage volume for that whole unit. Okay, so that's everything I need to do to set up the graywater scenario. I'll also set up a scenario for roof runoff. Okay, so now we move into the roof runoff scenario. Now you can see all those values for graywater were zeroed back out. Everything went back to default values. And since we're using only a small percentage of the stormwater and running roof runoff capture for this scenario, we'll need to change this value to, let's say, 30%. And to be consistent with what we did for graywater, we'll also look at combined flushing and irrigation. So I'll assume, again, 80% adoption to be consistent with that scenario. In this case, I'm going to include a storage volume of 1,000 gallons. That's a lot higher storage than would be typical with using rain barrels for harvesting rain, but this will be a storage that will allow us to make use of a higher amount of that generated stormwater. Okay, so I now have these 3 different scenarios here in addition to my default scenario, and I'm going to go ahead and save those scenarios. So those are all saving, and again at that subunit level, and then I can run the model from this point. Okay, so now we have that scenario data saved, and I can go ahead and do a new run of the model. And again, I'm going to go ahead and do a run from 2005 to 2015. Now here, we're really looking at, we're interested probably in projections of I'll go ahead and click run here. So we're interested in projections of demand over time. And what we're doing then with that year range that we're selecting is we're selecting 10 years of hydrologic data in order to run these various scenarios. So those now have all been run at that subunit level. So we can close this box. And now we can look at our graphs again. So I just clicked on, so I want to look at all of our scenarios. Okay, so now we see we have a lot going on with this graph. So I'll kind of guide through how you can look at some things individually as well. But most interesting when we look at this because we're kind of using historical data to make a future demand projection. So we'll look at this monthly average data. So we start over here with the default values for indoor and outdoor, the darkest blue and green. Then we move into the high efficiency homes, graywater reuse, and then roof runoff. So for example, with these, I can now look at a couple of these individually. So I can click on this and actually turn off some of these options. So I'm turning on and off so we can make comparisons between a fewer number of these. So I'll go ahead and turn off the gray water, and we'll just look at the comparison with roof runoff right now. So there we can see we use roof runoff to meet irrigation demand as well as some toilet demand. So we have some reduction in indoor demand as well as outdoor demand associated with that. Now, if we wanted to click back onto our graywater scenarios and add those back in, we see that we can further reduce demand, and that's for municipally delivered potable water for the graywater reuse scenario, which also use that for meeting toilet demand and outdoor demand. So we have a little more savings that we can potentially achieve with the graywater reuse scenario. And then we can go back and look again at our high efficiency homes. And there we see a pretty nice decrease in indoor demand, but the outdoor demand stays the same in that scenario. So that enables us to really make comparisons between all of these scenarios, and then some of those graphing capabilities help to make side-by-side comparisons as those may be needed. Okay, so now that we have looked at some of the scenarios related to water efficiency in terms of water conservation and reuse strategies, I'd like to also go ahead and show some scenarios where we look at population growth and land use change. So in order to do that, we again need to edit our practices, and we're going to create some new scenarios. The first one I'll look at is we'll do hot and dry. So now what we're going to do is create a scenario. We're going to look at a more hot and dry climate. So there's a couple of options here. We can here upload a file that has climate projections, or we can take our PRISM data that we've already uploaded and look at a temperature and precipitation offset based on that data. So what I'm going to do is look at an increase in temperature of 10%, which is pretty substantial, and a decrease in precipitation of 10% as well. Okay, so I've got those. So I've created my hot and dry scenario. And now I can also create a scenario of growth, let's call it. Okay, so for growth, then we can go into practices, and we will go into projections here. And let's go ahead and look at a 20% population growth, and assume that our households also increase by 20% with that growth. And then with that, we're likely to have a land use change. So what we'll do here, we'll assume that open area space stays the same. That would be common here in the city of Fort Collins, where a lot of that is conserved and not allowed for growth. So what we would see is potentially a change of low density area, where we are going to decrease that by, say, 20%, and then have a subsequent increase in medium density area of 10%, and then high density area also of 10%. Okay. We've got these set up so that we've got this decrease in low density area and increase in high density and medium density area. So those are the two scenarios I'm going to use to generate the projections for population growth and climate change. So I'm going to go ahead and save these now. And we're going to go ahead and run these scenarios again, and I'll use the same years of 2005 to 2015. And use the same outputs as we've been using so far. And I'm running this again, but you can see, even though we all still have all of these scenarios here, like roof runoff, graywater reuse, those are not rerunning because we didn't make any changes to those scenarios. So now the model's just taking time to only run our hot and dry and growth scenario. Okay, so we've run that now. And in this case, I'm going to select only those scenarios that I want to see. So that will be the default. We'll compare that with hot and dry, and then growth. Okay, so now we can look at these values, and again, I'm going to just select to look at the monthly averages. Okay, so again, on the far left here, we have our default or kind of baseline scenario. And then we move into this hot and dry, where we see, because of that decrease in precipitation and increase in temperature, there's an increase in outdoor demand. So we can also potentially overlay that with scenarios of xeriscape or changes in behavior of irrigation, which may be associated with rates or irrigation restrictions or things like that. So then finally over here, now we have our growth scenario. So that's the third one is for each month. So looking at those scenarios, interestingly now, because of that increased density in populations, we have higher population here, we have a higher indoor demand in each of our various months. But because we've changed the land use type from medium and high from low density to medium and high density, we now can observe a decrease in irrigation demand. So even though there was that growth in population, there's actually a decrease in demand from our baseline conditions. So it can be really interesting to start running various different scenarios of looking at how different land use changes and how we encourage new urban development can impact both our indoor and outdoor water demands. So here is where I can download these various graphs. So we can actually just take a JPEG image, for example, and use that and use it in a publication, which I've done frequently. You can download it as a PDF. We can also download the output data as a CSV file or an Excel file, open up that and work with it in any way that you would like to work with it individually to maybe run some different scenarios. So there's all sorts of ways that you can actually download the data that's used to generate these graphs and use it to conduct further analyses that you may be in. So with that, I am going to go ahead and close, and I'd be happy to take any questions that are out there.
One question I have, Sybil, is are people, if they wanted to consider, you can change the land use like based on percentage, but if folks have a future land use map with GIS layers, could that be loaded up in
Absolutely, thank you. So this integrated urban water model really has ultimate flexibility in terms of enabling a user to use these national databases or upload those any sort of layers that they may have that would include projections. So for example, when we first set up our project and we selected the NLCD database as where we were going to get our land use data from, at that point a user could instead upload any sort of GIS layers that they have that would be specific to their area, that may be even down to block or block group scale in terms of projections of land use changes in those areas, and then enable projections using those actual layers.
So you mentioned, scale of, what's the smallest scale this can do analysis of, and like what's the largest scale?
The most practical scale for smallest scale that IUWM can really work at would be the block level. You could envision selecting a household or a single building unit, but the block level is kind of the smaller scale. As far as a larger scale, like I mentioned, you could select a region and use the integrated urban water model to do projections of, say, counties or water service areas within that entire region, and it would automatically select to only include the urban areas within its analysis. So if a land was categorized as agriculture use or some sort of non-urban open space, then it would exclude that. So the scale can really be from that block level all the way up to a highly regional or even statewide analysis.
And you mentioned this model was calibrated with the city of Fort Collins. Is there is there ability to calibrate for other areas?
Sure. So future versions of IUWM, we intend to include an auto-calibrate function. However, in the interim, the way to do that is really to go and edit these various parameters like the home use profiles and based on the landscape irrigation and these land use percentages. There's also some things under irrigation here that depict behavior. So decrease in the irrigation achieved via advanced irrigation systems, there could be some of that adopted within a particular area. The percentage of evapotranspiration, so a lot of that is actually met through irrigation. A lot of these really capture some of the behaviors that people in a particular area would have. So these are default values that can work to get a reasonable estimate. However, if a person wanted to make this more specific to their area, they could modify these values and look at that, how the projections might compare with any observed data they may have, and kind of work on adjusting those until the observed and simulated data have a good match.
We have a question of, typically future growth involves development on currently unused parcels. How does that occur under the water service area boundary? Is growth assigned uniformly, or is it concentrated into mostly vacant land? And I guess would unused parcels be low density, or, well, you can address that.
Right. So the way that the growth goes is that you have either option. So if you use, in practices here, let's go back to projections as we talk about this. So if we just kind of say this population change is occurring, we use these interface settings to look at those changes in population and land use change, then what happens there is that is a uniform change throughout our entire modeled area. So in this case, since we're modeling the Fort Collins water service area, those changes apply universally or uniformly throughout the area. However, if we would like to concentrate those within particular subunits where we know we expect to potentially see more change, then we can go into the subunit table and begin to make those kind of changes there. So you can kind of do a quick and dirty run with the interface page, but get into a lot of details here with the subunit tables. And I should note that you would not necessarily have to manually go and change these tables. These tables, if you go into the map area here, we can actually upload tables into the model so that those would be used instead of these tables, and then you would see, as you open your subunit table, you would see those uploaded information appearing within your subunit table. So there are ways to do that quickly, but this is what enables a user to really look at a more focused plan or projection for land use change in population.